Good morning. Happy Pi Day. 3.14, 1519, I think. We'll start there. Happy Pi Day. It's not really a pie day, but it's a pie joke. Slice of pie is $2.50 in Jamaica and $3 in the Bahamas. These are the pirates of the Caribbean. All right. So can enjoy that it's Pi Day, maybe have some pie or something else circular to pi r. All right. So little erratum. Oops. Which means I made a mistake. Yeah. So last day when we did our calculation for the confidence interval, and I've got this the page here. Okay. I wrote it out properly. 0.657 times 1 minus 0.657, 0.668 times 1 minus 0.668. But then what did I manage to do? Then I did it correctly in the first line, but then in the second line, I should have had 1 minus 0.668. Now, luckily, right, 1 minus 0.6 is 0.4-ish. And so luckily that's kind of close to 0.6. So it didn't mess up our work that bad. But here, I'll just bring it in. So in the confidence interval calculation, I didn't do 1 minus 0.668, I think it was. I'll bring it in here. So I'm looking at here. This should be 1 minus 0.668. Which will change things all the way throughout, but we'll just leave it at that. You can try it, and I think I brushed it off as a rounding error in the slides, but presumably we would get closer to those values if I had done it correctly. Not a big deal. That's something that I would take just, half a mark off for on the test. So if you've shown your work, right? If you haven't shown your work, then it's hard for me to make adjustments. But yeah, just little mistake. The one thing that I want to note, I'll switch to pink for this. Okay, so on the assignments, it assumes that you're not rounding your values, okay? So keep all your decimal places until the very end. Keep all your decimal places until the end. This is fine if you're using something like Excel, right, where you can reference the cells, and that's easy enough. In fact, what I would encourage you to do is set up an Excel spreadsheet where you have a tab for 1 sample proportions, 2 sample proportions, and our new one today. But we're going to finish 2 sample proportions first. Okay, and so so you can have those spreadsheets because you're working online. You'll be able to just use those spreadsheets. What would you have to do? You would just have to change your p hat, your number of successes maybe, and your n, and then it should cascade through the spreadsheet. So that might be a nice tool to use. All right. Okay. So let's see here. What else did I want to say? I think that's good. Sorry. Don't want to forget something for later. Okay, so this is just, um, this is from last day. I did the calculation, I guess technically wrong. It's more sloppy than wrong. Calculation wrong. And I'll show you where. All right. I did this here, but then I didn't do it there. So this is good. And this is wrong. Other than that, should be fine. Okay. So we made a confidence interval. This is going to change a little bit, but that's okay. I think we still get a negative value and a positive value. So our conclusion stays the same, right? And just as a tiny bit of review, right? We were talking about two sample proportions. We introduced a confidence interval. We did a hypothesis test. We didn't quite finish the hypothesis test. And so here I'm going to say, review from last day, because we didn't quite finish the conclusion, but I just want to review the hypothesis test because it was the first time that we were seeing a hypothesis test for two sample proportions. Okay, so we had to state our hypotheses. I guess I should read the question. Do these data suggest that the proportion of all Duke students who would be bothered a great deal by the melting of the northern ice cap differs from the proportion of Americans who do? And so we wanted to state the hypotheses, which is that the proportion of Duke students minus the proportion of the US is 0. Now, what that means is that they're essentially the same. They're not significantly different. I want you to define group 1 and group 2. Now, because you guys are online, usually the question will say, let this be group 1 and let this be group 2. So then, of course, you have to follow that, right? And so, so that makes it a little bit easier. The proportion of Duke students minus the proportion of US is not equal to 0, right? And that's because we want to know if it differs from the proportion of Americans who do, right? And so if you added PUS to both sides here, then you would get P Duke is not equal to PUS, which is kind of easier to wrap your head around. The reason I use the minus here is because that is the value that we're comparing our point estimate to. In fact, it's where we got our point estimate from. And so either way you want to write these is fine, but I'm going to try to use just the subtraction version, right? P1 minus P2 is equal to 0. We introduce the conditions. Okay, and so what's nice is the conditions for a confidence interval and a hypothesis test for independence are the same, right? If we have randomly sampled, then we can assume that we have independence within the groups, but also between the groups, right? We have this added layer when we have two samples that we're dealing with. So then the normality condition, right, uses p hat. I guess I shouldn't really write on here, but I'll post it. So p hat is the pooled proportion. And this is on your formula sheet, right? It's x1 plus x2 over n1 plus n2, right? The number of successes in group 1 and 2 combined, right? That's why it's pooled over the total sample sizes, n1 plus n2. All of those are going to be greater than 10, so that's great. It's just something that we need to check. So, so we checked, and the normality condition is met, which just means that our sample size is large enough to assume that it follows a normal distribution. Right? And then in step 2, we said, okay, we're going to do the test, calculate the test statistic is really what we're saying. we want to know how far is the observed difference in proportions from zero, right? Because we do all our testing assuming H naught is true, and so an H naught is always going to be that P1 minus P2 is equal to zero. And so this is always zero. That's why it's not even on your formula sheet, because it's always going to be zero. P hat is the pooled proportion, right? Just as a reminder. And then Q hat is 1 minus P hat, of course. And we found this very small z, right? Very close to zero, which tells me that I'm not going to reject H naught, right? I need to move far enough away from zero to be able to reject H naught. And so we found this z, and then we're going to find the p-value. Of course, you could use software to find the p-value. In fact, the assignment makes you use the t-table and software. And so you'll need to be able to do both. Okay, so we said, okay, this table is a little bit misleading because technically we have a line at 0 here for z equals 0. That's the center. And then because we've just taken the absolute value, we're only looking at the positive values, right? And so the area in one tail is 0.5, and at 0, the area in two tails is 1, right? Oh, I do 2 all the time, and so I always get balloons. So then, how do we set this up, right? Especially because I encourage you to submit your work for test 2, right? Because then I can check against your answers and make sure if you've shown me that you had the right idea, then I can give you more part marks, right? And so I encourage you to write down your work properly, and this is how we would write that down. So we take the absolute value of z equal to negative 0.224, which is what we calculated. And we find when we try to place that on this line, on this z star line, we find that it falls somewhere between 0 and 0.674. That's fine. Which means our two-sided p-value, why is it two-sided? Two-sided because the alternative hypothesis is that P Duke minus PUS is not equal to 0, right? It's because of that not equal to. I'm not concerned about just one tail. I'm concerned about both, right? Not equal to. And so that's a really tricky concept that I know people struggle with a lot. But once you've got it, right, then you're good. Okay. And so that's difficult just because you have to go all the way back to step 1, and then you can figure out if you need a two-sided p-value or a one-sided p-value, right? So then if you have a two-sided p-value, then you want to make sure that you read these from right to left. I'm assuming that that you're using the same inequality. If you're comfortable with inequalities, you can mix them up. You can write this as the two-sided p-value is, I guess, less than 1 and greater than 0.5, if you want to read them from left to right. I just find that that's very confusing, and so I personally don't like inequalities, and so I just stick with the same one, and then I can just do that without thinking about what the inequality means, right? As long as I'm listing them from smallest to largest. Okay. I will take marks off if I see something like, well, you'll be marked wrong if I see something like the p-values between 1 and 0.5. That interval doesn't exist, right? You have to go from smallest to largest. Okay, and then I left you with my risque. Is this a meme? I don't know. Maybe. I need to figure out what makes a meme. But anyways, so if the p is low, then the null hypothesis must go. And the reason it is risque, but the reason I introduce this one is because it does help Okay, because what's our conclusion? If the p-value is small enough, right? So if it's low, then we have enough evidence to reject H naught. That's what this is saying. That's technically what Snoop wanted to say. He just didn't have the words. So if the p-value is small enough, right? Usually we use 0.05, so less than the alpha level, which has a default alpha is 0.05, right? But sometimes the questions will tell you what to use. If a question doesn't tell you what to use, you're going to use 0.05. That happens quite a bit where we don't even mention it, and then you'll use 0.05. So if the p-value is small enough, so less than 0.05, we have enough evidence to reject H naught in favor of HA. I guess in favor of HA. Okay. So our p-value, now we can use software, right? We can use norm.s.inverse of negative 0.2224, and that'll give you the area in the lower tail, right? And then you need to multiply that by 2. And so in lab 7, you'll practice that, but also in lab 8 using software. And I think, yeah, I make you do it on the assignments as well, because you have those skills now. Okay. Okay. So our conclusion, our p-value is somewhere between 0.5 and 1. I don't really care what that is. That's all greater than 0.05, right? In fact, you'll never have a time where it falls, but where 0.05 is somewhere in here, because, right, 0.05 is one of the cutoffs. And so you'll never cross that cutoff. So for us, this is kind of the end of the review, I guess. Used a lot of notes from last day. So our conclusion, I'll do it here. Our conclusion is going to look like this. For you, on test 2, it'll be a text box. And so I'm going to make you type out the answer, whereas a lot of the assignment, or all the assignments rather, you just click the right one, which is easier, obviously. But on the test, I need to see that you can actually write out your conclusion properly, and then I'll mark those afterwards, okay? And so the test is still a ways out, but I just want to highlight it as we go. So since now this is where you want to really show off all the things that you know, right? We're not going out of our way to find anything. I know I have a two-sided p-value, and I know what the range is for it, and so why not write that down? So since our two-sided p-value, oops, is between 0.5 and 1. And speaking of the test, I want to highlight that if you found the wrong p-value, right, you're not going to know that until I've marked your test, right? And so so as long as you follow through with whatever p-value you entered in the boxes, right, then that's fine, right? Just follow through with those answers, even if they're wrong, obviously. It's weird when you give me one answer and then you use a different answer in your conclusion. So, but I have seen it. So since our two-sided p-value is between 0.5 and 1, it is not less than and I don't think we were given an alpha level, and so I like to highlight that I'm assuming it's 0.05, so it's not less than our assumed alpha level of 0.05, which means we do not have enough evidence to reject H naught. If I'm not rejecting it, then I don't need to bring HA into this, right? Sorry, let me just grab a. I know, gross. I got sick and then I got better and now it's allergies or maybe hay fever. I don't know. They seem to be the same. One just lasts longer. Um, lucky me. Okay, so what does that mean in terms of the question? We're gonna reformat the question as an answer, right? That's our third part of our conclusion. And so I'm gonna go way back up here and I'm gonna say, I'm just gonna copy this part that I need. Paste image. Therefore, these data suggest that the proportion of all Duke students implies the population, right? Our conclusion's always in terms of the population, who would be bothered a great deal by the melting of the northern ice cap, differs from the proportion of all Americans who do, period. And then you can ignore that because that was just left over. So you reword the question as an answer. And oh no, haha, what did I do? I was acting as if we rejected H naught, but we didn't. So I need to alter this a little bit. Therefore, these data do not suggest that the proportion of all Duke students who would be bothered a great deal by the melting of the northern ice cap differs from the proportion of all Americans who do. There, that's important. Highlight that. Missed it. Okay. Nice. Good. Glad I caught that. I would have had to issue another erratum. No, thank you. At that point, it would be errata. Even worse. Okay. I kept this slide in here because it just shows the the calculation shorthand, right? And so it's the same question that we just did, but they've used a version of the Z table. Probably they used software instead, but you could use a Z table at negative 0.22 to find the area in the tail, right? And then that's going to be pretty close. But then you have to remember to multiply it by 2 because you have a two-sided test. Okay. So just as a recap, before we move on to very exciting, our next type of question, which it also introduces a new test statistic. And so a little recap here. We want to talk about P1, how it compares to P2. So I have two samples and I want to compare those sample proportions. Well, then my point estimate is P1 hat minus P2 hat. The conditions that we have to check is independence within the groups, which we can get by randomly sampling, and then the 10% condition is optional. For you, you'll have a list of conditions. Now, that list of conditions is going to be randomized, and it might not have all the conditions that you would need to check. And so what you're going to do is just select the ones that apply, right? So not necessarily all those conditions are going to be listed, right? So you need to know which ones to check off. Now, we also need independence between the groups. And then we need at least 10 successes and failures in each group. And this one is where it changes. right? For a confidence interval, we need the observed versus a hypothesis test, we need the expected, right? Or the hypothesized. And that's where we use the pooled proportion. Okay. And then we had the standard error just generically, right? But depending on if we had a confidence interval, then we use P1 hat and P2 hat in place of these P1s and P2s. And for a hypothesis test, then we are going to use, so here, we're only going to have this scenario. We can look at when when the difference between them is something not zero, but we're not going to do that. It's very rare. But so for us, we're going to use the pooled proportion, right, for both P1 and P2. Okay. So 6.3. You guys ready for this? So goodness, this is called a chi-squared test of goodness of fit. So here, this is goodness of fit, which sounds ridiculous because goodness is a word, but not in this way. And so, right? Oh my goodness. Goodness of fit, though, just sounds just very funny to me. But this, I want to start here. Chi is a Greek letter chi, which is a capital X. And so chi squared is chi squared. And chi, you want to be reading it as K-A-I, chi. If you call it chi, everyone's going to think you don't know what you're talking about. And so you want to make sure that you're using the right, you're saying it right. Okay, so it's got this kind of fancy X, capital X. And so chi-squared goodness of fit test is the next type of question. The type is a chi-squared goodness of fit. And maybe I'll write it out. Okay. This is our second test statistic that we're going to see, right? So far, we've only used Zs, right? And so far, we have only used Z as our test statistic. And chi-squared is a new test statistic. And we use chi-squareds mainly when we have 3 or more proportions. And so now, right, we're moving through. We started with and introduced all these concepts with one sample proportion. And then we said, okay, well, what if I have 2 sample proportions and I want to compare the two, right? And then now, what if I have 3 or more? Luckily, we can lump them all into one. So is a new test statistic used to analyze 3 or more proportions? Okay. So now we've moved into, we've kind of stepped it up. And one of the examples that I want to introduce here is kind of this fun slash exhausting sounding experiment that this guy, I guess Walter Frank Raphael Weldon, And so quite a long time ago, 1860 to 1906. And so he was an English evolutionary biologist and founder of biometry. Now, anything that ends in metry is statistics. And so um, there's biological statistics, right? And so here, this is uh, biology statistics, just kind of good to know. Yeah. Uh, econometrics is statistics related to economics. What else are there? They're all metrics. And so Biometrica is a journal, and I was gonna say I think it's still around, but I haven't checked, so could be a lie. Um, okay. And so in 1894, for some reason, he decided he wanted to see um he suspected, I'll tell you this. So, he suspected fives and sixes on a six-sided die would appear more often than the other sides of the die. Okay, and so he rolled 12 dice, 26,306 times, and then he recorded the number of fives or the sixes, which he considered to be a success, right? And so it was observed that fives or sixes occurred more often than expected, right? So just pay attention to, we have some observed information, right? And then we have some expected information. And that's going to be the key to a chi-squared test. But that's also been the name of the game so far, especially for hypothesis testing, right? I have some sample information and I want to compare it to my hypothesized information, right? So now I'm going to have some observed data and then my expected data. And so Pearson hypothesized that this was probably due to a construction of the dice. And so the thinking was that inexpensive dice have hollowed out pips, and since opposite sides add to 7, the face with 6 pips is lighter than the 1 pip. Okay. Because it's got more dug out of it. Now they've fixed that, obviously. Now they fill those holes, and so it doesn't matter. But back then it was a problem, right? And so just as a kind of a fun aside here, so Zachariah Labby at U of Chicago in 2009, he repeated this using a machine, of course, and a pip counting machine, so he wouldn't have to count these by himself. And there's a YouTube video if you want to watch it. Um, and so it took about 20 seconds per roll, and so he produces all this data. So what he was able to do, he was able to, instead of just talking about a success and a failure, which Weldon had to do, right? A 5 or a 6 was a success. Everything else, right? 1, 2, 3, 4, those are all failures, right? Now you've boiled it down to one sample proportion, right? And so that's what Weldon had to do because he didn't have the technology. So now Labby says, well, how about I have this machine just count how many what the faces all are. Okay, and so what he found was that the number of ones and sixes is quite a bit higher than 2, 3, 4, 5, right? And so here, this is the expected probability. Now, maybe I won't say probability because that could get confusing later. Okay, but so now this is what I'll call it the expected distribution, right? If I said, okay, I'm gonna do this experiment, what would we expect this distribution to look like if the if the dice were all fair? Well, we would expect 1 in 6, right? we would expect the 1 to appear 1 in 6 times, right? The 2 to appear 1 in 6 times, right? And so the expected distribution is 1/6 uh, for each die face. So what we can do is we can find expected counts, right? If we have this expected distribution, and in this case, we want to know if it's evenly distributed. Okay, I'll make a note here, right? We expect an even distribution. I'm going to show you this one where we expect an even distribution, but also another example where we expect some other distribution. So you need to be familiar with both types, but they behave the same way, so that's nice. So what we can do is we can find expected counts, okay? And so if Labby rolled 12 dice 26,306 times, why 6? Well, I guess it was groups of 6. 12. Anyways, whatever. If each side is equally likely to come up, how many ones, twos, and blah, 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 sixes would he expect to have observed? Well, 12 dice, 26,306 times, and then how many, right, evenly distributed? I'm going to skip to the answer here. Well, then we're dividing by 6. This is evenly distributed across the die faces. So what we're going to have is some observed count for each die face. Okay, and I'm gonna write O subscript I, right? This is O1, O2, O3, O4, O5, O6. Okay. And so here, this is O1, O2, right? Because these are all the observed counts. O3, O4, O5, O6. And then the total is your N. Okay. So what we could do, right, is 12 times 20, what was it? 26,306. That's your N. All right. That's how many times a die was rolled. We spread this evenly across the 6 categories. That's going to be our expected count. Okay, and our goal is to compare the observed versus the expected. Notice that here I have 6 categories, right? And so that's kind of neat. The expected, and I'll make a note here that here we have 6 categories to compare. 3 or more. Jumped right to 6. They're all the same, so they all behave the same way once you hit 3. Okay, and so the expected count, notice how it's all the same, right? We expect 52,612 in each of the, for each of the outcomes. Okay, so here's the expected count for 1, expected count for 2, expected count for 3, 4, 5, and 6. Notice how this is also the same N. Of course, they have to add to the same N. Okay. And so we talked about why these are different. right? And so our goal is to determine, well, 53,222 is different from 52,612, and 52,118 is different from 52,612. But cohesively, is there evidence that they're significantly different from each other? Right? And so we're not just looking at individual counts anymore. Now we're talking about, okay, these observed values, right? Some are going to be closer to the expected count than others, right? But overall, are they far enough away from the expected count to be considered significantly different? Okay. So our hypotheses. Okay. Now that I have more than two groups, it's going to be really hard to talk about, and especially in terms of the parameters, right? And so, luckily, we don't need to. Um, but what we're going to talk about is all those observed counts and how they compare to the expected distribution. And so, what we want to do these data provide convincing evidence of an inconsistency between the observed and expected counts? Okay. And so your null hypothesis generally is that there's no inconsistency between the observed and the expected. You have to assume that they're the same until you have proof otherwise. The observed counts follow the same distribution as the expected counts. Your alternative hypothesis, we're always going to talk about, okay, the observed counts do not follow the same distribution as the expected counts. In fact, maybe I'm going to hold off a little bit. I wanted to bring in the formula sheet. You have it. And so um, the hypotheses, just some notes about um, for a chi-squared goodness of fit test. I just want to talk about some general things. We're only going to do a hypothesis test. So no confidence intervals, which is kind of a bummer because at this point you're probably feeling comfortable with confidence intervals, but there's nothing to do an interval around, and so we don't. So we only do hypothesis testing. That's nice. In fact, we always do a two-sided test. We always do a two-sided test. As long as you remember that, that's fine, right? And so here, this makes it a two-sided test, right? If it's different. Yeah. And so, but the way that we're going to get this information, it doesn't actually matter, right? And so I'm going to show you why in a second. Okay. But here, in terms of our alternative hypothesis, it just means that we're just going to do the opposite. Okay. H naught and HA will be stated in words. It's on your formula sheet, so I will bring it in, but not quite yet. We're not quite ready yet. Okay. So to evaluate these hypotheses, then what we do is the same thing that we have been doing for hypothesis testing. We see how far those observed counts are from the expected counts. How we're going to do that is just slightly different, and that's where the chi-squared part comes in. Okay, but large deviations from what would be expected based on sampling variation or chance alone provides strong evidence for the alternative hypothesis, or rather against the null hypothesis. Maybe I would probably prefer uh, against the null hypothesis. Think about why I would change that. They sound the same, right? But we're always doing our testing assuming the null hypothesis is true, and so then I have evidence against the null hypothesis. Okay. It's called a goodness of fit test because we're evaluating how well the observed data fit the expected distribution. We expect some variation, but if it's within the realm of chance, then we say that, okay, they're basically the same. So let's just remind ourselves what any test statistic looks like. Okay. And so any test statistic, and we've only seen one so far, right? And so we have a point estimate minus the null value, and then the standard error of the point estimate. Okay. And so the chi-squared statistic is going to be very similar-ish. Okay. So when dealing with counts and, and investigating how far the observed counts are from the expected counts, then we use the chi-squared test statistic. Now the chi-squared test statistic looks like this. Chi-squared is the sum from I equals 1 to k, okay, across the categories, 1, 2, 3, 4, 5, 6 in our case, of the observed minus the expected, how far the observed is from the expected. And then we square that because otherwise when we sum things, they'll cancel out. And so we square them to make them positive and to amplify big differences. And then we divide by the expected count. Okay. And just as a note, K is the total number of cells or categories, or total number of categories. We need to know what K is because the shape of the distribution depends on the number of categories. Okay. So far, so good, though, right? Besides the summation, it's been a while since we did a summation, but I know you can do it. And don't worry, Excel has a nice, neat way of just taking the observed and the expected, and it just does all the work for you. But what we can do, right, is, so let's remind ourselves here, the chi-squared is the sum from I equals 1 to k all through the categories of the observed minus the expected, then squared, divided by the expected, which means we need to do this calculation for each category and then add them all up, right? And so do this calculation for each category and then add them all up. And that's going to be your chi-squared. Maybe now is the time to bring in from the formula sheet. So we did 2 sample proportions. That was a huge chunk of our formula sheet, mostly because we have the pooled proportion, which we tackled, and so now we're comfortable with that, and then it's not really that bad, right? And so now we move on to the next part of the formula sheet. Okay. I'll put it here and maybe zoom in for a bit. The chi-squared goodness of fit testing is just tiny because we're only doing a hypothesis test, and the null hypothesis is that the observed distribution equals the expected distribution. Okay. Now you're going to make that question specific, right? We would say the observed distribution of die faces equals the expected even distribution of die faces, right? And so you need to add a little flair, but generally this is the null hypothesis. And what's the alternative hypothesis? It's always going to be the negation, which is the observed distribution does not equal the expected distribution, right? The observed distribution of die faces observed, right? I said observed twice, I guess, does not equal the expected even distribution of die faces, right? And so that's what we're testing. Now I have these little subscripts I here, but you can ignore those if it makes sense to you to just add up all the components. And then the only new thing that we have here is that the degrees of freedom, df, is the degrees of freedom. Which determines the shape of the distribution. The df, the degrees of freedom. This is the first time we have seen degrees of freedom in passing where? We saw it on the t-table, so we will be using degrees of freedom more often. But this is the first time that we're seeing it, and it's just going to be a calculation, and it determines the shape of the distribution. The degrees of freedom determines the shape of the distribution. That's kind of weird. So that's going to take some explaining later, but just so you know, right, it's just going to be, what was K? K is the number of categories, right? And so we're going to have the number of categories minus 1 as our degrees of freedom. Okay? We can just kind of parking lot that for a little bit, but it's going to come back up. Okay? So now we're not going to do this calculation because this is a job for Excel, in my opinion. I don't like doing these. If I were to make you do these by hand, I would have maybe, just 3 categories, nothing crazy, right? Not 1, 2, 3, 4, 5, 6. So knowing now that we can say that K is the number of categories, well, here I have K equal to 6. I have 6 categories, right? Or 6 outcomes. I have the observed and the expected for each outcome, right? And I can do this calculation, the observed minus the expected, then square it, right? How far apart are they? That's a key part of any test statistic, right? And then we square that, and then we divide by the expected. And as far as I'm concerned, we can just take that as at face value. Let's just do what it tells us to do, right? You don't need to worry about why. And so each of these is going to yield some value, right? Indicating how far the observed is from the expected once we've adjusted some things. Then I add them all up and I get a chi-squared equal to 24.73. Okay, now what's difficult about chi-squared coming from a z is, well, z is always fixed, right? So that's a nice property of z, and that is why we start there. Chi-squared can be quite large, depending on the degrees of freedom, right? 24.73 might be very large, or it might not be very large at all, right? And so it's hard to wrap our head around a chi-squared of 24.73 without some probability calculation, okay? And so let's just talk about, just briefly, in the observed minus the expected squared divided by E, this is what they're talking about here. Why do we square it? And I mentioned it in passing, right? But squaring the difference between the observed and the expected does two things. So um, it makes values positive, okay, but also amplifies large differences, right? And so here I summarize this as it amplifies large differences. We've seen this before, right, in our standard deviation calculation. Standard deviation calculation. Yeah. Okay. We're getting there. So the chi-squared distribution, yeah, and there's a couple of edits I need to make on this slide, and so that's maybe I should have deleted it, but I wanted to keep the degrees of freedom point here. And so in order to determine if the chi-squared statistic, so 24.73, we calculated is considered unusually high or not, we need to first describe its distribution. So where does it come from? The chi-squared distribution has just one parameter, right? So one thing that influences the shape, center, and spread of the distribution, and that's the degrees of freedom. And so the degrees of freedom, which influences the shape, center, and spread of the distribution. Okay, and so depending on the number of categories, that's going to determine the shape, but also the area in the tail, which is the p-value, right? And so what this means is the number of categories determines the shape and therefore the p-value. Yeah. So far, now this is where it's more of a note because we haven't seen three others. This is from a different a layout. We've changed it. And so we've seen one other continuous distribution. Okay. And so we will see the T distribution and we will see the F distribution. And so, but we have seen Z. That's the normal distribution, which is unimodal and symmetric with two parameters, right? We need to know the mean and the standard deviation in order to know the shape, center, and spread, right? And that's always going to be the things that we need. We haven't seen the T distribution, but we will next week. Okay, so that's good. And the F distribution, I don't think we'll have time to see it until the very end of the course. Okay? But we will see. So Z is the normal distribution, right? That's where we're comfortable so far. And so let's see here. So we've seen one, it says 3, but it also gives us a nice overview of where we're headed, right? So these distributions are all chi-squared, okay? With different degrees of freedom. So with 2 degrees of freedom, 4 degrees of freedom, and 9 degrees of freedom. So let's just talk about how the solid line to the dashed line to the dotted line changes. So the solid line looks like this. Okay. 2 degrees of freedom. Very smushed up against 0, and then basically an exponential decline. Okay. Then we increase the degrees of freedom, right? And here I just want to make a note. Recall that the degrees of freedom is k minus 1. So it's the number of categories minus 1. So here I have 3 categories, the very smallest number of categories that we could have. Here I have 5 categories. Here I have 10 categories, right? That's crazy, but doable with Excel. What would you have to do? If you had 10 categories, you'd have to do the observed minus the expected squared divided by expected 10 times over. That sounds terrible. Right. And so here, right, we've got this distribution now at 4 degrees of freedom, right? It looks skewed to the right, positively skewed. Notice that they all start at 0. Okay, and so that's a property of the chi-squared, is that it always starts at 0 and you can't have any negative values. And so then we increase the degrees of freedom. Now I have 10 categories, so 9 degrees of freedom, and it's starting to look more and more normally distributed, right? And that is a property of the chi-squared. But let's just see which of the following is false. I hate these. But the slide maker seems to like them. As the degrees of freedom increases, the center of the chi-squared distribution increases as well. Well, let's just think about that. So here the center is here, right? I'll tell you where it is. Then the center at 4 degrees of freedom has moved further out. In fact, look, it's kind of close. Then for 9 degrees of freedom, it's increased even more. And so that is true. Right? As the degrees of freedom, the variability of the chi-squared distribution increases as well. And so the variability is the spread, right? And that's hard to look at, but at 2 degrees of freedom, we have very little spread. And then here, 4 degrees of freedom, spread out a little bit more, right? 9 degrees of freedom, now we're spanning quite a bit and then we've got the center and we've got more room on either side. And so that's true as well. Just tell you that it's true. The shape of the chi-squared distribution becomes more skewed as the degrees of freedom increases. Well, that's not true, right? The opposite is true. Right? The opposite is true. Mm. So how do we find areas under the curve? The area under the curve is the p-value, right? In fact, the p-value is the tail area under the chi-squared distribution. Okay, the tail area. We only have one tail. There is only one tail, right? The upper tail. So that's okay. That's going to be our p-value. We're not really worried about one-sided, two-sided anymore because we're always just going to have that tail area as our p-value. And our alternative hypothesis is always just going to be the negation of the null hypothesis, right? And so that's okay. And so we can use technology, right? We can use Excel to find the probability, or we can use a chi-squared probability table. Now, on your formula sheet, oops, you have a mini version, and this is all you'll need. I'll make sure that this is all you need, right? Or I guess if you need more, I'll give you a bigger table, but they all behave the same way. And so on your formula sheet, you have this. Okay. Now, what are these values? So the upper tail area is the p-value, right? And so this is going to be the p-value. And these values right? The degrees of freedom is k minus 1, the number of groups minus 1. And so what's interesting about the chi-squared that we haven't seen before is if you have 4 groups, then you have 3 degrees of freedom. You ignore all the rest. Then what's in this table is very similar to the Z star line on, oops, on the T table, only because I don't want to have it going across the next page. So these are chi-squared values. Huh? So you're stuck at some degrees of freedom, and then you ignore the rest, just like you've been ignoring the rest of the T table, right? And then we try to place our calculated chi-squared somewhere along this line. Okay, so that's the same as what we've been doing for Z's, right, to find the p-values recently. So just a little bit of practice. Now they give us uh, a bigger table, right? I gave you a condensed table, it's all you'll need, and more degrees of freedom. Of course, there's tables upon tables upon tables that you could find. And so here we have 30, and it's not obvious, but we want to find the area in the tail, right? And so here we have 10 degrees of freedom, meaning we have 11 categories. And so at 10 degrees of freedom in this table excerpt, we're stuck on this line, right? And we're going to try to place 30 somewhere on this line. Do, 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 do. Okay, here. Chi-squared equals 30 would be somewhere there. Okay. What can we say? It's somewhere between 0 and 0.001, or just less than 0.001, right? What if we had chi-squared is 17? 17, and we're told that the degrees of freedom is 9. Oh, let's see here. Can I use the table? Okay, yeah, can. You know what? To keep it clean, just delete that temporarily. Put it back. So now I have 9 degrees of freedom, and I'm trying to place 17 on this line, right? 17 is going to fall, and of course the chi-squareds are all increasing as I move across, right? That's the same as before. And so our chi-squared of 17 is somewhere between, right? Chi-squared is 17 is somewhere between 16.92 and 19.68, which means the tail area, or the p-value, is going to be somewhere between 0.02 and 0.05. Has that same property that we're now used to dealing with, right? Where the area in the tail is getting smaller and smaller as I move further out into the tail, right? And so it's somewhere between 0.02 and 0.05. Okay. In a way, I find that the chi-squared table is a lot easier to deal with than the other probabilities. And I don't know why, I can't explain it. Okay, so we could also use software. So this is R, if this is R code. Oops. We could use Excel. Excel has a chi-squared dot dist, I think, of some chi-squared. Yeah, you might have to look it up. But of course, Excel can calculate a chi-squared probability. What would it need? Probably the chi-squared and probably the degrees of freedom, of course. Okay. Uh, we already did this one. We decided it was less than 0.001. Using software, we can find that. So here, using software, we can find a more precise probability, but it is less than 0.001, right? 0.00085, blah, 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 is less than 0.001. Okay, so back to our example here. Do these data provide convincing evidence of an inconsistency between the observed and the expected counts? And so here, our null hypothesis has to be that there isn't until we have proof otherwise. And so there's no inconsistency between the observed and the expected counts, which means that the observed counts follow the same distribution as the expected counts. And the alternative is the flip side of that, that they don't follow the same distribution. I don't know where this came from. Was 24.73, I want to say. It was a long time ago, I guess. Where is it? Yeah, here it was 24.73, so I'm not sure what happened. Use 24.67 from here on. Okay, just because otherwise I'd have to correct all the slides everywhere, and that would be difficult. Okay, we need to know the degrees of freedom so that we can find the p-value, right? We've done the test. That's step 2. Do the test. So chi-squared is 24.67, although we found 7.3, but that's okay. And so all we need is the degrees of freedom, and the degrees of freedom is k minus 1, which is 6 minus 1, which is 5. Okay. And so now we have 5 degrees of freedom, so that's great. The p-value is going to be the tail area above the test statistic. Okay? And from the formula sheet, and I wonder if I still have it. Nope. From the formula sheet, let's use that table. Just for some practice using this condensed table, right? We had 5 degrees of freedom and 24.67. If I try to place that somewhere here, then 24.67 would fall here. So using the table on the formula sheet, the p-value, I'll say the p-value is less than 0.005, right? 0.005 here, or you could say between 0 and 0.005, or between 0 and 0.005. That's the same. Okay? Less than 0.005 or between 0 and 0.005. Okay? That's a very small p-value. So what's our conclusion? Our p-value, I'll use the one that we did, is less than 0.005. If we had a bigger table, we could get even more precise, but that's okay. That's very small. At 5% significance level, what does that mean? It means alpha is 0.05, which is our default anyways. What's the conclusion of the hypothesis test? Well, I'm definitely going to reject H naught. And so I'll eliminate any that fail to reject H naught. right? Reject H naught. The data provide convincing evidence that the dice are fair, but the null hypothesis says that um, that it is fair, and the alternative, which I'm rejecting H naught in favor of, says that the dice are biased. And so here, this one, right? The dice are fair. Well, this is the same as the null hypothesis. But if you're rejecting the null hypothesis, then you can't go against that. And so you're going to reject H naught. The data provide convincing evidence that the dice are biased, right? We're not following that even distribution. So just a little bit of fun wrap up here. Let's see, my 1 minute left. Right, there's just a couple of notes, but nothing in statistics land. Okay. But right, the p-value is the area in the tail, right? And so let's just talk about the conditions for the chi-squared test. We have to have independence. So every count that you have has to be independent of the other counts. There's a sample size condition, so this is the newest one. We have to have at least 5 expected cases in each category. That's the newest one. And then it goes without saying that the degrees of freedom has to be more than 1, which means that K has to be more than 3. K, therefore K must be 3 or more. Right? Strictly greater than 1, which means 2 or more. And so if we have 2 degrees of freedom, I have 3 categories. Okay. Now here, I want you to review this example on your own for more practice, right? Where we don't assume an even distribution. Now I want to know, okay, I have this hypothesized distribution. Do my counts follow that? And it'll work through it, blah, blah, blah. And then 6.4 will be on a bonus assignment not covered in class, which means chapter 7 is what we're starting next week. All right, I'm all out of time. If you have any questions, let me know. Otherwise, have a great weekend, and I'll see you next week. Stop this.